So today we will be solving maybe one more problem related to nilpotent group. Uh, Before we start, maybe just recall what we have done before. So let's try to define nilpotent group once more. Let's try to recall the definition. So what we had is we had a group G. So there is a, let G be a group, and we defined this sequence of chain of subgroups, right? Which was, how was it? There was Z naught G is a subgroup of Z1G is a subgroup of Z2G, and so on. And how was this chain defined? It was defined in the following way. Z naught G was, what was Z naught G? Does anyone remember?
E.
Yes, Z naught G is just the trivial group by definition, and Z1G is the center of the group, ZG. And then what will be Z2G? Z2G is actually you take the group G quotient Z1G, take the center of that group, that will be of the form some Z2G mod Z1G. So this is my third term of the group, and so on. We define it in a recursive way, that Zi plus 1G by Zig is the center of G mod G quotient Zig. So I think you must have been accustomed. So I sometimes say G mod Zig, sometimes I say G quotient Zig, which are both the same thing. Sometimes we use the word quotient, sometimes we use mod. Okay. Uh, and by mod I mean modulo, not this mod. Okay, not the absolute value mod. Okay, I mean modulo. So and when is the group nilpotent? So G is nilpotent if there exists some C which is a natural number or zero, such that ZC of G is G, right? Okay. So this is the definition of a nilpotent group. And let's also quickly recall the equivalent conditions of a nilpotent group. Okay. So I'm not going to write it in big details. So what was the theorem? If if G has to be a finite group first of all, and order of G is P1 and 1, P2 and 2, PSNS. Okay. By the way, I have somehow got this bad habit of writing too many dots. Okay. The ones who wants to become teacher or anyway should only put 3 dots. Okay. Uh, that's the usual convention. Don't put as many as dots you want. Okay. Okay. So if G is a group of this order, and PIs are the uh, PIs are the silo PI subgroup of order PI power Ni. Okay, then uh, then the following are equivalent. Okay, then the following are equivalent. So what was it? What were the condition? Can someone quickly recall? So first is G is nilpotent.
G is normal in G is a subgroup of G. H is subgroup of G.
Yeah. If H is a subgroup of G, then H is a proper subgroup of the normalizer of H. That is the norm. See, you should understand that. Remember that the normalizer always contains H. Normalizer of H will always contain. So what does this theorem, this statement say? That normalizer has at least one more element other than the elements of H. That is what this theorem is, this statement is saying. Okay. Third is the subgroups Pi are normal in G, and fourth is G is actually isomorphic to the external product of P1, yeah, external direct product of. See, again I wrote four dots. Five dots actually. I shouldn't write. Okay, of this of the silo subgroups. Okay, and again here what you should remember is that whether G is nilpotent or not, in any case, G is actually equal to the product of this groups subgroups. But what the theorem, what the statement demands it, that it should be uh, external product of silo subgroups. Okay, so with this short quick recap of what we have done so far, let's solve a problem. Okay, so let me write down. So problem, let G be a finite group. Prove that G is nilpotent if and only if for all A comma B in G, whenever the orders of, if the orders of A and B are co-prime, that is GCD of order of A and order of B are co-prime, then A and B commutes, that is AB equals B. Quite interesting question, problem, right? So let us try to prove it. Okay, so again, this is the same story. Okay, every time I will say that let order of G is P1 and 1, P2 and 2. Yes, this time I have put only three dots. PS and S, where PIs are distinct primes, and let PI be the silo PI subgroup of order Pi power Ni. Okay, so this part is this is a common stuff we have to keep writing it. Okay, so let's now try to prove the theorem. So let's prove the forward direction. Okay, so let's prove the forward direction. So what do we need to prove? We have now given that G is nilpotent, and we need to show that if two elements orders are co-prime, then the elements commute. Okay, so given is now given G is nilpotent. Okay, so again, if you recall from this equivalent conditions, I think the main one which we keep using will be the third and the fourth one. These are the important one which will be quite helpful for us. Okay, so if G is nilpotent, then this will imply that G is actually isomorphic to P1 external product P2, so on PS. And also let's remember that PIs are actually normal in G. Okay. Now what do we want to show? That we want to show that if we have to take two elements A and B in G, and we have to show if their orders are co-prime, then they should commute. Okay, so let A is in G. Now the point is, because G is this external product of P1 to PS, we can write A equals some G1. We can write A, we can, write in the sense we can identify A with a S tuple, with a ordered pair with S elements, right? Let A uh, this, and let B is a element which is H1, H2, HS. So we are using heavily that G is nilpotent, and hence G is a external product of the silo subgroups. Okay, so let's write down this P1. Okay, let's now let me go to the next slide. Now, what is order of A? Does anyone remember? We did this in the, we did this few weeks back. If A is G1, G2, GS, what is order of A equals? No, this is not there in your just the immediate previous classes. Can someone answer what will be order of A?
Of G1
G1 to G.
Yes, Vivek, can you repeat it one more time?
Isn't it the LCM of the order of G1 to GS?
Exactly. So this order of A is the LCM of order of G1, order of G2 to order of GS, and similarly order of B is LCM of order of H1, order of H2, order of HS. Okay. Now I claim that if GCD of order of A and order of B is 1, then GCD of order of GI, order of HI is also 1 for all I from 1 to S. Okay, so let's try to prove this. Okay, so proof of claim. And we will prove it by the method of contradiction, that we will assume that suppose it not happens. Okay, so suppose the conclusion doesn't happen, then what can we say? If this doesn't happen means what? That means the GCD is not equal to 1 for all I. That means there exists some I for which the GCD is bigger than 1, right? So if possible, let there exist K which is between 1 to S such that GCD of order of GK order of HK is D, and D is some number more than 1, right? Suppose this happens, okay? Now this GCD is what is the meaning of GCD? GCD is greatest common divisor, right? So what is D? D is first of all a divisor. It is the greatest common divisor, but it is a divisor for both order of GK and order of HK. So D divides order of GK. Now order of GK has to divide. See, again, now you have to understand what is LCM. LCM is what? LCM is lowest common multiple, right? Now, will not order of GK will divide LCM of order of G1, order of G2, order of GK? Is Does everyone agree with this?
Yes.
Because it's a common multiple, right? So G order of G1 has to divide the LCM, order of G2 has to divide the LCM, and so on. Now in a similar fashion we can say D divides order of HK, and which should divide the LCM of order of H1, order of H2, comma order of, sorry, this is HS not K, HS, GS and HS, okay? But what does this mean? There is a number, okay, and this is what, by the way, this is my order of A, and this is order of B. So what does this mean? That we have a number D which divides order A and order B, okay? And remember that this D is more than 1. So what can it say? What can you say? Can you say, can the GCD of order A, order B be 1?
No.
What is GCD? GCD is the greatest common divisor. So you already have a divisor, common divisor, which is more than 1. So this will say that the GCD cannot be 1. So this, let me write, this will imply that the GCD of order A and order B actually it's more than D. What we can say is, okay, let me write like that. It is more than D, and D is more than 1, okay? Which contradicts the fact that GCD of order of A and order of B is 1. So we have proved our claim, and let's just recall what is our claim again. Our claim was this, that this each component's order for both elements has to be uh, co-prime. Okay, so let's remember this, and let us proceed. So now see this GI and HI belongs to which subgroup? Let me show you again. Where does AB belongs to? So see this. Uh, AB AB is of the form G1 G. I mean, A is a ordered pair G1 to GS. B is a ordered pair H1 to HS. So where do you think this each of the GIs and HIs belong to? Which subgroup will it belong?
PI.
Very good. It will belong to PI. So let us remember this and see then what can we conclude. Can we derive some information from this? So this Gi and Hi belongs to Pi. So this will say that order of Gi and order of Hi should divide the order of Pi. Any elements order divides the order of the group. And this, uh, what is this group's order? Pi power Ni, right?
Nine.
So which will imply that order of Gi is of the form some Pi power k, and order of Hi is the form some Pi power L, where both k and L ranges from 0 to Ni. Okay. Now these are their orders. Okay, some Pi power k and Pi power L, and I am saying their GCD. And what have we proved just before? That their GCD is 1, right? So let's write down here. So we just proved also, we just proved the GCD of order of Hi and order of Gi is 1. Okay. Now, can you say when can it happen? When is it possible to happen? So one order is, let's say, some 2 power, I mean 2 power something. The other order is also 2 power something. Okay. Now these orders are co-prime. When can it happen? Suppose one is 2 power 2, the other is 2 power 5. Then what is the GCD of these two orders?
4.
2 power
2 power 2, right?
2
2
power
power the
2.
2 power the lowest power. Then suppose one is 2 power 10, one is 2 power 3. What is the GCD?
2 power
3.
3.
So
3.
when is it possible that the GCD will be 1? What should be the scenario?
K,
One
comma
should
L is equal
be,
to 0.
Correct. One
one
of
of
the
the
orders
orders
should be
one.
1, right? So this will imply
power
either order of Gi is 2 power 0, or order of Hi is 2 power 0.
2 power
What will this imply? When this is 1, right? Which is 1. So which element's order is 1? There's only one element in a group whose order is 1, right?
right.
So this will either imply Gi is either E or Hi is either E. Okay. See, we are almost done. So by the way, remember that when I say E, I actually mean is the, is the E in the PIs, not in G. Okay. So that means either Gi is E or Hi is E. Okay. Do you see the now the proof is done? So this will also imply that Gi Hi is Hi Gi, and this will happen for all I equals 1 to S, because one of them is identity. So whether, so it has to commute, right? You know that identity commutes with anything, right? So now we are almost done, right? Because why? We wanted to show, now let us again recall that what we wanted to show. We wanted to show that AB is BA, right? So therefore, now what is AB? Now AB is what? AB is, A is G1, A is G1, G2, GS, B is H1, H2, HS. So this is G1, H1, G2, H2, G3, H3, GS, HS. And then you can just change the order because of just what we proved. And that is nothing but PA. So are we done with this part? Is everyone okay with this?
Yes, sir.
Okay, okay.
Yes, sir.
So let's try to prove the converse. Okay. So, uh, so we need to show G is nilpotent. Okay, and our idea will be to show that again we recall what are the equivalent conditions. Let's quickly recall. See, I said that this third and the fourth one is much useful. In this case, we will use this. That we will show that PIs are normal in G, and we will conclude that hence G is nilpotent. Okay, so okay, I'm not. Let's not write that. So we. So let me say that it is enough to show. It is enough to show PIs are nilpotent, normal in G for all I from 1 to S. Okay. So before I prove that PI is normal, let's have a quick observation which will help us to prove that PI is normal in G. Okay. So let some GI is in PI and G GZ, not GZL, okay, GZ is in PJ, okay, and let's say I is not equal to J, okay. Now, what will be order of G1, GI? Order of GI will obviously divide order of PI, which is PI power Ni, and order of GZ, G, yeah, it's little difficult. GZ, okay, divides order of Pj, which is Pj power Nj, okay, and remember that Pi and Pj are different, okay. Pi is different than Pj, that is they are different primes, okay, and are primes. So, can you have the GCD of order of G? What can you say about the order of GI? Or what can you say about the GCD of order of GI and order of GZ? See, understand. So let's say PI is some 5, okay, and let's say this is equal to 5 power 10, and this is equal to let's say 11 power 20, right? So the order of GI will be 5 power something lesser than 10 or equal to
Yes.
10, and order of GZ will be 11 power
11
something
power.
lesser than equal to 10. Now, what can be their GCD?
They are primes.
Suppose 2 power
1.
7 and 11 power 3. What is the GCD?
1.
1. So whatever is the order, the GCD has to be 1. Correct? Does everyone agrees with this? Now, what is my hypothesis? If GCD, so let's look at the hypothesis again. Let's look back to our question. Uh, what is my hypothesis? If GCD of two elements are
AB
1,
equals BA.
then AB equals BA. That means what? GI equals. So this will imply that GI GZ equals GZ GI for all I not equal to J, right? That means what? If you take, now you know that, let's again go back to the first slide. You know that your G is, what I mean is, excuse me, just a moment. Yeah, what I mean is, you know that your G is of this form, right? P1 cross P2 cross PS. and elements look like this, right? So what I'm saying is, if you take a element from two different parts, two different Scilopy subgroups, they has to commute, okay, which is going to play a very important role, okay. So with this understanding, let us now try to prove that Pi is normal in G. So let's now show Pi is normal in G. And you know how to show something is normal, right? So let's do this. So let G equals G1, wait 1 second. Let's G equals G1, G2, G3 dot Gs is element of G, which is equal to P1, P2, Ps. Remember, for this you don't need nilpotency. This is always true. Don't need nilpotent C of G. This we can write always. Remember that, okay? And let's say Pi is in uh, the subgroup Pi. Okay. Now consider G inverse Pi G. Okay. So what is G inverse? G inverse is G1, G2, GS inverse Pi G1, G2, GS. Now what is G1, G2, GS inverse? The famous shoe socks lemma. What is it? So it is GS inverse, GS minus 1 inverse, dot dot dot, G2 inverse, G1 inverse, and then Pi G1, G2, GS. Now you see something very nice happens. Now just look at this portion. Okay, you see in this portion, Pi belongs to where? Pi belongs to Pi, and G1 belongs to where? G1 belongs to P1, right? See, because I have written G of the form G1, G2, GS, right? So I should have said it here, but it means that GI belongs to Pi, right? So G1 belongs to P1 and this belongs to Pi. So if I is not equal to 1, what will happen? I can, this, this part, uh, this part I can switch. I can write it as Pi and G1 inverse, and then G1 is here, right? What will happen then? G1 inverse will cancel out, isn't it? Correct? So do you realize that uh, all terms Pi will commute with all GIs other than the, I mean, so let me write down in the next slide. So uh, Pi will commute with all GKs or maybe GJs where I is not equal to J, and and this kind of situation, Gj inverse Pi Gj will be actually Pi Gj inverse Gj, which will be uh, just Pi. Okay. Therefore, whatever we wrote will be equal to actually Gi inverse Pi Gi, which is obviously an element of Pi. The reason is Pi is a subgroup of G. Therefore, Pi is nilpotent in G, and therefore Pi is normal in G. Therefore, G is nilpotent. Okay, so the proof is over.